The sphere has an infinite radius and is concentric with the Earth. They gave this sphere a name, celestial sphere, and we still call it that today. From Earth, it appears to move from east to west, one complete rotation every 24 hours. Over the years, astronomers have selected 57 easily identifiable stars on the celestial sphere for navigational purposes. The rest can be disregarded. In addition, navigators have traditionally used the planets Venus, Mars, Jupiter, and Saturn, the Earth's moon, and the sun. To understand how these celestial bodies are used for navigation, you must first review some basic terminology. Let's begin on the Earth, or the terrestrial sphere, as it is sometimes called. The Earth rotates around an imaginary line called the axis. The intersection of the axis and the surface of the sphere are designated the north and south poles. A plane that cuts through the center of the Earth creates an arc on the Earth's surface known as a great circle. There can be any number of great circles. A plane that includes the Earth's axis creates a great circle known as a meridian. There are an infinite number of meridians, and they all pass through the north and south poles. The meridian that passes through the Royal Observatory at Greenwich, England, has been selected as the prime meridian. It is the meridian used as the origin for measurement of longitude. Longitude is the angular distance measured at the poles from the prime meridian to another meridian, east or west, from 0 degrees to 180 degrees. The equator is the great circle perpendicular to the Earth's axis. It is represented by the letter Q. Latitude is the angular distance from the equator measured along a meridian north or south from 0 degrees to 90 degrees. The great circle distance of the arc along the Earth's surface is called arc distance. It can also be translated into linear distance. 1 minute of arc equals 1 nautical mile, or 1 degree equals 60 miles. Thus, the 90 degrees from the equator to the North Pole is actually 5,400 nautical miles. A point at 45 degrees latitude is 2,700 nautical miles from the equator. Parallels of latitude are lines on the Earth's surface whose planes are parallel to the equator. The parallels are combined with meridians to provide the grid system that helps you position yourself on the surface of the Earth. There is a similar grid system on the celestial sphere. To begin with, there is an axis, simply an extension of the Earth's axis. The points of intersection of the extended axis and the celestial sphere are called the celestial north and south poles. Polaris, or the North Star, is approximately at the celestial North Pole, and the rest of the sphere appears to revolve around it. A plane through the center of the celestial sphere produces a great circle on the surface. Great circles containing the axis are called celestial meridians when they are projections of terrestrial meridians on the celestial sphere. They are extensions of the meridians on Earth. For example, the terrestrial Greenwich meridian, or prime meridian, extends out to the celestial sphere to become what is called the celestial meridian of Greenwich, or the prime celestial meridian. The great circle perpendicular to the axis is called the celestial equator, or sometimes the equinoctial. It is an extension of the Earth's equator. Celestial latitude is called declination. It is the angular measure from the celestial equator, north or south, to a given point on the celestial sphere from 0 to 90 degrees. There are parallels of declination on the celestial sphere similar to parallels of latitude on Earth. When combined with celestial meridians, they form a celestial grid comparable to our terrestrial grid system. Now we must relate the two. First, assume you are at a specific point on the Earth. The point directly overhead on the celestial sphere is called your zenith. Your latitude and longitude coordinates on Earth are similar to the coordinates of your zenith on the celestial sphere. Conversely, every celestial body has a point on the Earth directly below it. This is called the geographic position, or GP, of the celestial body. Sometimes it is called the subpoint. If you were at the geographic position of Polaris, the star would be directly overhead at your zenith, and you would be near the North Pole. Similarly, if you were at the equator and the sun was directly overhead at your zenith, you would be at the sun's GP. This principle applies to any celestial body, the moon, a planet, a star, or the sun. You are at that body's GP when it is directly overhead at your zenith. Now at this point, we must introduce the concept of apparent motion between the terrestrial and celestial spheres. Using ancient man's concept that the Earth is stationary, we imagine the celestial bodies on the celestial sphere to rotate from east to west. The rate of motion is 1 degree of arc every 4 minutes, or 15 degrees every hour, or 360 degrees every 24 hours. This rotation introduces another term, hour circle, to help locate these bodies at a given time. It is a great circle on the celestial sphere containing the axis and a given celestial body. Let's assume that at a given moment, the sun's hour circle is coincidental with the prime celestial meridian. 4 minutes later, it will be 1 degree to the west of the prime celestial meridian. An hour later, it will be 15 degrees to the west, and so on. We have used the sun as an example, but the apparent motion is common to all celestial bodies. Their hour circles are constantly rotating from east to west. The term that describes the amount of rotation is called hour angle. Hour angle is always measured westerly from a reference point through 360 degrees. In celestial navigation, we use 3 specific hour angles: Greenwich, local, and sidereal, depending on the origin of the measurement. The first of these, Greenwich hour angle, is comparable to longitude on Earth, except GHA is only measured in a westerly direction through 360 degrees, while longitude is always measured east or west 180 degrees from the Greenwich meridian. Using the sun as an example, we may measure its Greenwich hour angle at any given moment from the prime celestial meridian westerly to the hour circle of the sun. This angle is referred to as GHA sun. The Air Almanac lists the GHA of the sun, moon, and planets for any date and time this data is desired. The second of the 3 hour angles, local hour angle, is measured from the observer's celestial meridian westerly to the hour circle of the celestial body. If the observer is at 90 degrees west and the GHA of the sun is 120 degrees, then LHA sun is 30 degrees. The LHA of other bodies observed for celestial navigation may be computed: the moon, Venus, Jupiter, Mars, Saturn. But when stars are used for navigational purposes, another reference must be used to determine their position. It is the prime hour circle, the hour circle of the sun at the intersection of its elliptical path and the celestial equator as the sun transits from south to north declination. This is the vernal equinox, the first day of spring. The prime hour circle is called by several other names, but they all mean the same thing: the hour circle through the point where the sun's declination is 0. The angular measure from the prime celestial meridian to the hour circle of Aries, the prime hour circle, is called the GHA of Aries. It is listed in the Air Almanac for every date and time. But what the navigator needs to know, of course, is the GHA of the star he is observing. The GHAs of the 57 navigational stars could be tabulated, just as has been done with the sun, the moon, and the planets. but it would require a monstrous publication. Instead, the navigator uses the GHA of Aries plus the third of the 3 hour angles, sidereal hour angle. SHA is the angular measure from the prime hour circle to that of a given star. This angle never changes. This is important. Remember, stars appear to move because of the Earth's rotation. However, they do not change their position relative to one another. So even though the celestial sphere appears to be moving, the prime hour circle and the hour circles of the stars maintain constant relative positions. So the sidereal hour angles, as well as the declinations of the various stars, are considered fixed. SHA and declination for the 57 navigational stars are listed on the inside front cover of the Air Almanac. The navigator can determine the GHA for any navigational star merely by adding its fixed SHA to the GHA of Aries for the time desired. Now let's sum up. When you determine a celestial body's GHA and declination, you know its geographic position or subpoint on Earth. Then, when you actually take a measurement that indicates your range from the celestial body's geographic position or subpoint, you can determine a line of position on the Earth's surface. To determine this line of position, we will utilize the horizon system, which will be demonstrated in part 2 of this series. When a celestial body's Greenwich hour angle, or GHA, and declination are determined, its geographic position, or subpoint on Earth, is known. Obviously, if from a measurement you find the celestial body to be directly overhead at your zenith, you would know you were at the GP of the body, and your latitude and longitude would be the same as the body's celestial coordinates. But the chances of this happening are very rare. Usually, you are some distance away from the GP of the celestial body. When this situation exists, you are only able to determine a line of position. To determine this line of position, we utilize the horizon system. When we extend a line from your position in one direction to your zenith, and in the other direction through the center of the Earth, out the other side, and on out to the celestial sphere again, we have what is called a zenith-nadir axis. A great circle plane perpendicular to the zenith-nadir axis is called the celestial horizon. In effect, we are creating a new reference system with your position at the center. Great circles containing the zenith-nadir axis are called vertical circles. Now we must determine where the celestial body is on the vertical circle. To do this, you must recognize that the distances of space are so great that light from a celestial body arrives at the Earth in a narrow band of rays that can be considered parallel. From your geometry, you remember that a straight line cuts across parallel planes at the same angle. So an angle observed at the surface of the Earth is really the same as that at the center. Suppose the angle is 0 degrees. The celestial body will appear to be on the celestial horizon. This is just a way of saying that the thickness of the Earth can be disregarded in celestial computations. The measured angle of a celestial body from the celestial horizon is called altitude. It is indicated by the letter H. Altitude, when computed, is called HC. It is called HS when it is sighted through a sextant, and it is called HO when the sextant reading is corrected for instrument and observation error. It is easy to confuse altitude with declination, but remember, altitude is measured from your celestial horizon. Declination is measured from the celestial equator. For example, the declination of Polaris is approximately 90 degrees. But its altitude varies depending on your location on Earth. It stands to reason that the angle of altitude will always be less than 90 degrees, unless the celestial body is directly overhead. The farther you move away from the GP of a body, the smaller the angle of altitude. The closer you come, the larger the angle. The difference between 90 degrees and the observed altitude of a celestial body is called co-altitude, or zenith distance. This is an important angle to remember when you begin to use celestial navigation to plot a line of position, because zenith distance can also be expressed in nautical miles on the surface of the Earth. Let's say you have obtained a sextant observation of 70 degrees on a star. You can see that a 70-degree measurement can be made from any number of points. You immediately know that you are someplace on this circle, called a circle of equal altitude. This is the first step toward determining a line of position. To find out how far away you are in nautical miles, merely compute the zenith distance. 90 degrees minus 70 degrees observed altitude equals 20 degrees. Therefore, 20 degrees arc distance separates your position on Earth from the GP of the star. Since 1 degree equals 60 nautical miles, you are 1,200 miles from the GP of the star. To find your precise position on this circle of equal altitude, you must take an observation of another body to determine a fixed position. 2 intersections will be noted, but only one will be near your DR position. A third observation will confirm your actual position. So far, we have reviewed with you the terrestrial grid system and the celestial grid system. They are related by your zenith and the geographic position of an observed celestial body. The GHA and declination of a celestial body can be translated into latitude and longitude of its GP on Earth. GHA and declination of the Sun, the Moon, and the planets Venus, Jupiter, and Saturn are available in the Air Almanac for given dates and times. The GHA of Aries is also given, along with the sidereal hour angles for the 57 stars. We have also discussed the horizon system and how it is used to locate a line of position from the geographic position of an observed celestial body. When you note the altitude, you know you are somewhere on a circle of equal altitude around the GP of the observed body. The technique of actually plotting a line of position depends on the observed altitude of the celestial body. If it is 85 degrees or more, the zenith distance formula shows that you are within 300 nautical miles of the GP, and you can actually plot the circle of equal altitude on the navigator's chart. But if the altitude is less than 85 degrees, and it usually will be, you would need a chart too large to fit in your aircraft. So you must use a different technique. It is called the intercept method, and it will be discussed in part 3 of this series. There are 2 methods of resolving celestial observations to determine a line of position. The first should be used if the altitude of the observed celestial body is 85 degrees or more. Let's say it is 87 degrees. In other words, it is almost directly overhead or near your zenith. The angular distance of the body to your zenith is called zenith distance. In this case, it equals 90 degrees minus 87, or 3 degrees. This can be translated into linear distance on Earth, the distance in nautical miles from the body's geographic position to your position. 1 degree equals 60 nautical miles, so 3 degrees equals 180 nautical miles. To locate your line of position, you must first determine the coordinates of the GP. The GHA and declination of the celestial body can be found in the Air Almanac. They can be translated into latitude and longitude of the GP on Earth. You then locate this point on your chart. With your dividers, you can measure off 180 nautical miles. Then, you can scribe a circle or segment known as a circle of equal altitude. This becomes a celestial line of position. You are somewhere on its circumference. To get a fix, you must take at least one more observation of a celestial body, preferably two. This is a very simple method to locate or plot a line of position. Usually, however, you will be observing celestial bodies with altitudes less than 85 degrees. Bodies whose geographic positions will be hundreds or even thousands of miles away from your own position. Theoretically, you could use the first method to plot your line of position, if you had a large enough chart. But obviously, you need an alternate. There is one, and it is called the intercept method. As with the first method, it may begin with an observation with the sextant to determine the sighted altitude, or HS, of a celestial body above the horizon, and a notation of the date and Greenwich Mean Time of the observation. This observation enables you to determine corrected observed altitude, or HO, an important factor you will use in a few moments. Now you begin computations by finding the geographic position of the observed celestial body. This means determining its GHA and declination on the celestial sphere. Then, translating those coordinates to latitude and longitude on Earth. Then you assume a position for yourself on Earth, somewhere near your DR position. In the intercept method of celestial solution, you determine and locate your actual line of position relative to your assumed position, instead of the GP of the celestial body. This involves the solution of a celestial triangle brought down to Earth. The points of the celestial triangle are the celestial body, the celestial pole of the hemisphere you are operating in, and the zenith of your AP. On Earth, the points become your AP, the GP of the celestial body, and the appropriate pole. As you remember from your geometry, if you know the length of two sides and the included angle of any triangle, you can quickly determine the other side and angles. If you know the declination, you know this side. Codeclination, or polar distance of the observed celestial body. 90 degrees minus the declination. If you know the latitude of your assumed position, you know this side. Colatitude. 90 degrees minus the latitude. This angle is the LHA, local hour angle, of the celestial body. It is measured from the celestial meridian of your AP westerly to the hour circle of the celestial body. In this situation, LHA of the celestial body equals its GHA minus the longitude of your AP. If your AP were here, east of the prime celestial meridian, you would add the longitude of your assumed position to the GHA of the celestial body to get the LHA. So if your AP is east longitude, you add the longitude to GHA to get LHA. If it is west longitude, you subtract longitude from GHA to get the LHA of the body. However, in this west longitude situation, where the AP is west of the observed celestial body, LHA is this angle. Remember, LHA is always measured westerly 360 degrees. In this case, you can compute LHA by taking the GHA of the body, adding 360 degrees, then subtracting the longitude west of the AP. The remainder is LHA of the celestial body. But back to the first AP we considered and the solution of its celestial triangle. Most of the computations have been done by mathematicians who have created tables designed for three inputs: LHA of the celestial body, whole degree of latitude of your assumed position, and declination of the celestial body. With these three factors, you can turn to your HO 249 site reduction tables to find two important factors. First, the computed altitude, called HC, from your assumed position to the celestial body. HC is the altitude you would observe with your sextant if you were actually at your assumed position. When you have HC, you can compute the co-altitude, or zenith distance, the third side of your celestial triangle. This gives you the linear distance from the GP of the celestial body to your AP. Or, in other words, the radius of the circle of equal altitude from the GP to your AP. The HO 249 tables also give azimuth, the interior angle of the triangle of your assumed position. This angle is referred to as Z. You must then convert Z to true azimuth, or ZN, an angle measured clockwise from true north. A reminder for converting Z to ZN is found in the upper and lower left-hand corners of each page in the HO 249 tables. If true azimuth were plotted on a chart, you would have a line running from your AP toward the GP of the celestial body with a segment of the circle of equal altitude perpendicular to it through the AP. This segment is represented by a straight line because the radius of the circle is so great. With ZN, or true azimuth, you can now begin to locate your actual line of position. You know HC, the computed altitude of your assumed position. You also know HO, the corrected HS, or sighted altitude of your actual position. Suppose these are the actual figures. HO is 45 minutes of angle greater than HC, or, in other words, there are 45 nautical miles difference in radius between the circles of equal altitude, measured along the true azimuth line. But in what direction? Remember the basic principle of altitude measurement. The larger the angle, the closer you are to the GP. The lesser the angle, the farther you are away. In practical terms, if your HO is less than the HC of your assumed position, you are farther away from the GP of the celestial body. If HO is more, you are toward or closer to it. Just remember ho, mo, to. Ho, more, toward. Ho, mo, to. Think of the happy Japanese navigator, Lieutenant Homo-to, smiling over your shoulder. In this case, HO is 45 minutes of angle more than HC. Remembering Homo-to, you know you are 45 nautical miles toward the GP of the celestial body. This is called intercept. The line of position is plotted as a straight line representing a segment of your circle of equal altitude with a barb at either end of the LOP, the name of the source on top, and the time of observation beneath. Two other LOPs derived from observations of two other celestial bodies will give you a positive fix. This is how the intercept method works in theory. We will see how it works in practice in Part 4 of this series. In Film 3 of this series, we examined the principles behind the intercept method for plotting a line of position. Now we will apply the method to actual problems. You need your sextant, a timepiece, an air almanac, HO 249 site reduction table for declination, and an HO 249 site form to record your findings. There are 3 steps required to establish a celestial line of position: observation, computation, and plotting. The sequence of these steps may be altered depending on which of 2 approaches you select. In the pre-computation method, computation is made for a predetermined time. Then an observation is made at that time, followed by plotting. But we'll use the post-computation method with the observation first. In our example, let's assume an observation was taken on the sun at 1630 GMT. Record your observations on the site form. Body, sun. GMT 1630. Date, 24 January. HS of sun, 32 degrees, 21 minutes. Normally, several corrections, such as atmospheric refractions and instrument error, will be made to the sextant reading. But in this case, we'll assume no corrections. Thus, HO is the same as HS. Now you're ready for the computation stage. Remember, you will be using tables to solve a celestial triangle. To do so, you will need to know the declination of the observed body, the sun, the latitude of your assumed position, and the local hour angle between them. To begin, you turn to your air almanac. Open to the page for January 24. Look down the Greenwich Mean Time column to 1630 and read off the GHA of the sun, 64 degrees, 26.8 minutes, or rounded off, 64 degrees, 27 minutes. Declination is 19 degrees, 8 minutes south. List GHA and declination on the site form. Here's where the sun is on the celestial sphere, 64 degrees, 27 minutes west of the prime celestial meridian, 19 degrees, 8 minutes south of the equinoctial or celestial equator. This is one point of your celestial triangle. When the GP sun is translated into latitude and longitude on the Earth, you have one point of your triangle on Earth. Your DR position determines another. Let's say your DR position is 27 degrees, 42 minutes north latitude and 97 degrees, 12 minutes west longitude. Since you are operating in the northern hemisphere, the North Pole becomes the second point on your celestial triangle. The third point is your assumed position. It could be the same as your DR position, but since the HO 249 tables are arranged for whole numbers of latitude, you give your assumed position the nearest whole degree of latitude, or 28 degrees north. You use a longitude for your AP that, when added to or subtracted from the GHA of the celestial body, will result in a whole number for local hour angle. Your DR longitude is 97 degrees, 12 minutes west of Greenwich. You are west of the sun. Remember, figuring LHA in this situation gets a bit tricky. Since LHA is always measured westerly through 360 degrees, this is the angle you are seeking. To compute the LHA of the sun, you must first take the GHA sun and add 360 degrees. This gives you 424 degrees, 27 minutes. LHA is this figure minus longitude. The longitude of your DR position is 97 degrees, 12 minutes west. But remember, the The longitude of your assumed position should be a figure that, when subtracted from GHA Sun, will produce an integral degree of LHA. If you use 97 degrees 27 minutes, the difference will be an LHA Sun of 327 degrees. Now you have established your assumed position. 28 degrees north latitude and 97 degrees 27 minutes west longitude. This, then, is your celestial triangle translated into usable components on Earth. You know this side, the co-latitude of your assumed position, 90 degrees minus 28, or 62 degrees. This side is the declination, or polar distance of the Sun. South 19 degrees 8 minutes plus 90 degrees, since it is located in the southern portion of the celestial sphere. 109 degrees 8 minutes. And this is a known angle, 360 degrees minus your LHA, or 33 degrees. Now, with two sides and the included angle known, you can compute the linear distance side and the true azimuth angle, the elements you need to draw a line of position. In actual practice, you never have to draw the triangle itself. All you need are three elements related to it: the whole degree of latitude of your assumed position, declination of the observed celestial body, and the Sun's LHA. The other information you need, HC and Z, is found in the declination volumes of HO 249 site reduction tables. You enter HO 249 with latitude first. Turn to the pages headed 28 degrees. There you have your choice of two tables. One headed Declination Contrary Name to Latitude, and the other headed Declination Same Name as Latitude. Since your AP latitude is north and the Sun's declination is south, you use the Contrary Name to Latitude table. Note there are two LHA columns, the one on the left for smaller angles, the one on the right for larger angles. Use the right-hand column to find 327 degrees. Move across the tables to the column for the whole degree of declination of the Sun, 19 degrees, and you read HC for 19 degrees as 33 degrees 11 minutes. A D, or correction factor, of minus 49, which we'll discuss in a moment, and an azimuth angle, Z, of 142 degrees. The D value is the total difference, or change, in minutes of altitude between the declination of 19 degrees and the declination of 20 degrees. The Sun's declination is 19 degrees 8 minutes, so you must account for the extra 8 minutes of declination. You could use a simple interpolation formula. 8 minutes of declination over 60 equals X, the amount of correction necessary, over the D value of 49. Or X equals approximately 6.5, rounded off to 7. However, this formula is more easily solved by turning to correction table 5 in the back of HO 249. Enter the table with the D value of 49 and move down the minute column to 8. The correction value is read off as 7. Since the D correction value had been a minus quantity, 7 should be subtracted from 33 degrees 11 minutes, the HC of an even 19 degrees. So HC for 19 degrees 8 minutes is 33 degrees 4 minutes. This figure should be entered as HC on your site form. Now for ZN, or true azimuth. The upper left-hand corner of the HO 249 page tells how to compute ZN, your true bearing from Z. You are in north latitudes. LHA is greater than 180 degrees, so ZN equals Z. LHA less than 180 degrees, Zn equals 360 minus Z. In this case, your LHA was 327 degrees, more than 180 degrees. So Zn equals Z, 142 degrees. The lower left-hand corner of the page lists instructions for south latitude positions. Okay, now let's turn back to your site form. Insert Zn. All the other figures should also have been entered. Now all that's left is to compare HC with HO to determine the intercept distance, and whether you are actually away from or toward the observed celestial body from your assumed position. Remember Ho-Mo-To, the happy Japanese navigator. His name is printed right on your site form. If HO is more than HC, you are toward the celestial body from your assumed position. HO is 32 degrees 21 minutes. Less than the HC of 33 degrees 4 minutes. So you are away from your assumed position. When you subtract HO from HC, you find a difference of 43 minutes, or you are away 43 nautical miles. Now let's look at the celestial triangle a moment and see what we have discovered. Here is your assumed position. You know it is on a circle of equal altitude from the sun. You also know that your actual position is somewhere on another circle of equal altitude with a radius of 43 miles greater. And you know the intercept distance is measured on a true azimuth line of 142 degrees. Now let's see how this is plotted. Plotting is really very simple. Here is your AP. Lay out a line along the true azimuth, 142 degrees, away from the celestial body. Don't draw the line. Merely use your dividers to scale off 43 nautical miles from your AP. Draw a line at right angles to the Zn line. This is a segment of the circle of equal altitude of your actual position at the time of the observation. Put barbs on each end. This is your celestial LOP. Label it with the source above the line and the time of the observation below. One or more additional LOPs will give you a fixed position. Of course, you will have to take the motion of your aircraft and its altitude into account. You will learn how that is done later. Meanwhile, if you understand the principle of the intercept method, you will be able to work any celestial navigation problem. Let's review the key points briefly once more. It all begins with an observation of a celestial body to determine an observed altitude, HO. Then comes computation. The mathematics of the intercept method involve the solution of a celestial triangle brought down to Earth. The points are the GP of an observed celestial body, an assumed position near your DR, and the pole of the hemisphere you are operating in. In theory, if you know two sides and the included angle, you can compute the other side and angles. The mathematics are done for you. All you need to know is the latitude of your assumed position, the declination of the observed celestial body, and the local hour angle of the celestial body. Determining LHA is the tricky part of the problem solving. In a situation like this, where the AP is in west longitude and east of the GP of the celestial body, LHA equals GHA of the body minus the west longitude of the AP. If the AP is in east longitude, LHA equals GHA plus the east longitude. If the AP is west of the celestial body, the LHA is this angle. Enter HO 249 with latitude of your AP, the declination of the observed celestial body, and the LHA of the body. This enables you to find HC, the computed altitude of the celestial body, Z, the azimuth or bearing angle, and ZN, the true azimuth. By comparing HC with HO, you can determine the intercept distance between your actual circle of equal altitude and that of your AP. Remember HO-MO-TO. If HO is more, you are toward the GP of the celestial body. With this information, plotting is easy. You have a celestial LOP. With one or more others, you have a fix. With a little practice, you can easily master the principle of celestial navigation to determine your position. And you will always have the reassurance of knowing you can use this age-old navigational technique should events ever make it necessary.
From the first dawn of civilization, down to the age of 20th century science, man has looked to the stars for the determination of time, for the observation of position, and for knowledge concerning the basic forces of the universe. And now, he boldly turns his thoughts on the possibility of voyages toward the distant spheres. Within the past decade, the naturally radiant and the sunlight-reflecting bodies of the celestial vault have been joined by a new class of glowing, pinpoint objects of the night, the artificial satellites of Earth. In the periodic motions of certain of these tiny luminous objects, against the background of fixed stars, a powerful new tool has been acquired for the determination of the Earth's true dimensions, form, and figure, and extremely accurate distances over its surface. A valuable new method has been realized for the location of precise geographic positions, and to the science of geodesy has been added a distinctly more accurate procedure for determining the deviation of the Earth's actual figure, the geoid, from the assumed mathematical figure, the ellipsoid. The story of man's efforts to explore and to secure positional and dimensional knowledge of the globe on which he lives begins in remote antiquity. As early as the 4th century BC, the Greek navigator Pytheas of Massilia ventured through the Pillars of Hercules and reached the coasts of ancient Britannia. Around the year 1000 AD, the Norse seaman and adventurer Leif Erikson, with eyes turned toward the skies, but with his craft drifting on the wind-driven currents of the sea, first sailed the waters of the uncharted Atlantic and attained the shores of present-day Labrador. In the same historical period, but in another ocean and another clime, early Polynesian voyagers sailed onto the vastness of the Pacific in open outrigger canoes, guided only by crude bamboo stick charts depicting the islands, current patterns, and prevailing drifts, and by their observation of the winds, the flights of birds, the arrangement of clouds over islands, and the positions and arrangements of the stars. Over the course of many centuries, ignorance gave way before knowledge. And superstition and fallacy yielded before scientific fact and reality. It was in a treatise written around the year 1187 that an English monk, Alexander Neckham, first mentioned the practical application of the directive property of a magnet in compass form. By placing a small lodestone or a magnetized needle upon a floating object in a bowl of water, and as a later improvement, by pivoting a magnetized needle at its center in a horizontal plane, a magnetic compass was produced, which aligned itself with the north and south magnetic poles of the Earth. About the year 1500, the Portuguese geographer, Juan de la Cosa, prepared a chart on which the American coastline was shown for the first time, and on which compass directions were provided for the benefit of the navigator. But the compass directions did not always hold true. It was found that the pointing of a magnetic compass needle was subject to a varying deflection from true geographic north as a ship sailed across the ocean. Mariners must be taught a knowledge of this variable compass deflection from true north, which became known as magnetic variation or declination. Continuously widening voyages of exploration led to the development of special charts showing the values of variation of the compass at far-flung points over the globe. As the years passed, a more precise means of determining positions at sea became necessary. The earlier invention of the cross staff by Levi Ben Gershon in 1342, followed by Hadley's quadrant in 1731, and the sextant about 1757, had made possible the observation of the angular altitudes of celestial bodies above the sea horizon. From the observed altitude of the pole star with small corrections, or from the altitudes of other celestial objects, as the declinations of these objects became available in tables, the navigator could determine his angular distance directly north or south of the equator, the geographic latitude. Change of position in an east-west direction, or longitude, could be determined at this early time only by the method of lunar distances discovered by Regiomontanus in the late 15th century, and by dead reckoning based on an estimation of the ship's course and distance run. Prior to the invention of Hadley's quadrant in 1731, there was no really accurate means of observing the meridian transit of the sun at sea, and therefore of determining the local time. Nor until the invention of the portable chronometer by the Englishman John Harrison in 1735 and his timekeeper number 4 of 1759 was there any method of maintaining close accuracy in timekeeping over many weeks at sea. The modern form of marine chronometer, mounted in gimbals to compensate for ship's roll and pitch, was developed in 1765 by Pierre Leroy of France. This device, in conjunction with quadrant observations of the sun and improved astronomical tables, made it possible to determine accurate longitudes at sea. Although the positions of ships could now be determined on clear days within an accuracy of several miles, the longitudes of shore positions were not accurately known, a circumstance which, especially in a fog and at night, presented a considerable hazard for the navigator. The determination of precise longitudes could only be made by means of an astronomical or geodetic transit instrument. No sizable and permanently mounted instrument of this type existed in America prior to about 1835. Because of the inadequate charting of the coasts and the inaccurate geographic positions of the landfalls their navigators sought, ships might come in danger of foundering in the immediate coastal waters. These considerable inaccuracies in position determination, together with the geographic expansion of our young nation, made it imperative to secure a more precise and extended survey of the lands, the boundaries, and the seacoasts of these United States.
What has already been done may be regarded as introductory to a general survey of the coasts of the United States under authority of the government. With a correct chart of every part of the coast, our seamen would no longer be under the necessity of relying on the imperfect or erroneous accounts given of our coast by foreign navigators. I hope the lives of our seamen, the interests of our merchants, and the benefits to the revenue will be regarded as affording ample compensation for making a complete survey of the coasts of the United States at the public expense.
On February 10th, 1807, at the recommendation of President Thomas Jefferson, an act was passed
to cause a survey to be taken of the coasts of the United States, in which shall be designated the islands and shoals and places of anchorage.
Under the active leadership of its first superintendent, Ferdinand R. Hassler, new and more precise techniques of position measurement and of surveying on land and by sea were developed. From these simple beginnings, the present U.S. Coast and Geodetic Survey, the oldest government scientific organization in this country, was founded to assist coastal shipping and commerce between the states. On land, too, the problems connected with the determination of accurate position became more important as vast new territories were annexed and necessary boundaries were established. Only by observations of the sun, moon, planets, or stars at precisely known instants of time, as recorded at different positions on the Earth, could the difference in longitude, and hence the east-west distance in miles between these observing stations, be determined. By 1846, the perfection of the Morse telegraph register, first conceived in 1837, made possible a comparison of the time difference, and hence the difference in longitude, between two chronometers at two widely separated stations by means of signals transmitted over a telegraph wire between the two stations. The respective local times at the two stations were determined by observation of the meridian transit times of selected stars and comparison with a portable chronometer according to a procedure known as the eye and ear method. But the vast expanse of ocean precluded the accurate determination of the distances between the continents. The first successful laying of the Atlantic cable in 1866 by the ship Great Eastern made possible a new and more accurate comparison of longitude difference between England and North America by means of electrical signals transmitted along the ocean floor, together with precise celestial observations for local time at the two end points of the cable. Coast and Geodetic Survey technicians were waiting at both ends of the line, in Valentia, Ireland, and in Heart's Content, Newfoundland, even as the cable was pulled ashore. With the assistance of the U.S. Naval Observatory, time signals from Greenwich were tied in with Washington, D.C. And from that time on, Coast and Geodetic Survey charts carried the resulting longitude corrections. The invention of radio offered the potential for transmission of time signals at the speed of light, without the restriction of connecting wire or cable. Transmission of radio time signals provided, in turn, an improved method for the comparison of differences in local clock times between two widely separated stations. From observations of the time difference, the difference in longitude between the receiving and transmitting stations could readily be calculated. As early as 1922, the regular transmission of time ticks from Navy radio station NAA in Arlington, Virginia, was in use by the Coast and Geodetic Survey for the determination of longitude differences between its field stations and Washington, D.C. The 20th century also brought the advent of aircraft flight. At first, over relatively small distances, later, over transcontinental and intercontinental paths. As the years passed, direct great circle flights across the vast polar wastelands became a reality. Upward, man flew to altitudes where accurate identification of even gross topographic features was rendered difficult, and often confused by blowing or drifting snow. Again, the stars became the unfailing guide of the aerial navigator, supplemented by flight planning and en route charts designed to meet the needs of the jet age. A significant new requirement for availability of in-flight navigational checkpoints on long-range intercontinental flights over polar and oceanic regions came with the age of supersonic jet aircraft, with planes variously designed to carry passengers, cargo, or military crew at speeds of from 1,800 to 2,000 miles per hour, or more than twice the speed of sound. Many factors, such as extended hours of daylight, a complete absence or a low observing altitude of the sun, uncertain winds, magnetic interference, a lack of cultural objects, and frequently impaired ground visibility, all combine to make aerial navigation in polar regions a special problem. A sufficient supply of fuel is the sustaining lifeblood of the voracious jet engines. Time-consuming course corrections result in excessive fuel consumption. Thus, over a transpolar route in particular, refined navigational techniques permitting an optimum course without waste in fuel are requisite to global flight in the vast aerial ocean. Through broad advances in navigation science, together with matching improvements in aeronautical charts, this challenge is being met. Transpolar flights now arrive and depart safely on schedule. And so, as the world grows figuratively smaller, further scientific programs, both to enhance the accuracy of positions and distances over its surface, and to fill in the existing gaps for navigation in polar and oceanic regions, follow as a natural accompaniment. The ultimate accuracy in geographic position determination, as well as the ability to reach such remote geographic areas, has been demonstrated as feasible through a worldwide network of satellite triangulation stations, established to provide global coverage according to a well-coordinated plan. Such a goal for worldwide, equivalent first-order position determination has been set by the Coast and Geodetic Survey, now a component of the Environmental Science Services Administration of the U.S. Department of Commerce. In an age of burgeoning international commerce, constantly expanding horizons for foreign trade, and the availability of nuclear-powered, cargo-carrying ocean vessels, close consideration must be given to methods for enhancing transportation of the mineral resources, agricultural commodities, and other products of world trade. Once visionary concepts are now being practically applied to permit the recovery and exploitation of natural resources from the ocean floor. Passages beneath the Arctic ice cap by nuclear-powered submarines have already become a reality. The polar route reduces by many days the coast-to-coast transportation time between such areas as Alaska and Europe. The industrial ports of Alaska and the Pacific Northwest are thousands of miles closer to the European continent by way of this polar route, compared with passage through the Panama Canal. Huge nuclear-powered cargo-carrying submarines offer for the future a means of transporting oil, grain, lumber, minerals, and other bulk commodities along undersea shipping lanes, safe from the influence of surface winds and storms. An appropriate example may therefore be cited of one application of satellite triangulation to the future course of world commerce in the accurate position fixing of remote navigational, weather, oceanographic, and homing beacons. To facilitate marine navigation, signal transmitting devices known as transponders and placed in accurately established positions upon seamounts or submarine plateaus at the bottom of the sea, or mounted on underwater stable platforms secured to the ocean floor, can serve as homing beacons, both for surface vessels and for the navigation of undersea cargo carriers, pursuing continuously submerged, optimally planned courses toward their destinations. Instrumented deep-sea buoys moored to the ocean floor can also provide valuable navigational and meteorological data to aircraft flying above such long stretches of open water. Portable and recoverable radio beacons, dropped by parachute in polar regions, can be used as mid-course checkpoints for planes navigating transpolar routes. The accuracy and position determination attainable for these various types of beacons, whose location may also be constantly shifting, is dependent upon the availability of adequate position-fixing ties between these beacons and their reference, or base stations, as well as a high degree of positional accuracy in the base stations to which they are referred. While, both on sea and land, such data ties can be accomplished across the relatively short distances between beacons and base stations by standard electronic position fixing or surveying methods, the necessary accuracy of position of the base station demands the use of a portable observational system yielding a strength in observational data equivalent to that of a first-order ground triangulation survey. But the seas are broad. Oceanic island groups are few. And both the polar ice cap beacons and those in or on the deep sea may be separated from existing accurately surveyed continental reference positions by gaps too wide to permit precise positional tie-ins by methods of traverse, ground triangulation, or electronic position determination. Even in remote, outpost locations, the desired degree of accuracy is available in the satellite triangulation system, with certain distinctive advantages being provided over standard geodetic methods. Conventional first-order geodetic control procedures involve measurement of the altitudes of celestial objects with respect to the terrestrial horizon, which is defined by the direction of gravity. The Earth's figure is, rather than a true sphere, an oblate spheroid or ellipsoid, produced by the centrifugal force of its axial rotation. For purposes of accurate surveying, a geometric figure formed by the average surface of the seas is adopted. This irregular surface, everywhere perpendicular to the direction of gravity, is called the geoid. Because sources of varying local mass attraction are provided by the Earth's high mountains and by the basins of the seas, the direction of the vertical, that of a plumb line freely suspended, is slightly influenced by such variations in the local attraction of gravity. The leveling bubble of a precision surveying instrument is affected in proportionate degree. By contrast, the observation of an artificial satellite against a background of stars provides a system of measurement that can be tied to the surface of the Earth, but which is entirely independent of the varying direction of the vertical on the Earth's surface. Since the satellite positions are measured on photographic plates, with respect to the apparent tracks of stars, which are produced by the rotation of the Earth, these positions are affected only by the orientation of the Earth's axis of rotation in space, and are determined in the equatorial system of star coordinates, so-called right ascension and declination. Such celestial positions are completely independent of any variations of the Earth's surface from a spherical figure. One of the basic geometric principles of satellite triangulation lies in a phenomenon known as parallax, which may be demonstrated by a simple example. A fact of everyday familiarity to a person sighting past a nearby object toward a more distant background is that when his angle of view changes, so does the apparent position of the nearby object with respect to that background. A movement of the eye to the left results in an apparent displacement of the nearby object to the right. This same principle may be applied to a body located above the observer's head, the fixed background now being the starry vault of the sky. Any object between the observer and the distant stars will be projected against a slightly different portion of this star background when seen by two observers located at widely separated points on the Earth's surface. Although equivalent results can be obtained by multiple observations from only two stations at a time in the satellite triangulation method, simultaneous observation from three or more widely spaced stations provides improved geometrical strength in the solutions. In the observing technique of satellite triangulation, precision satellite cameras are located at each of these ground stations to photograph the apparent positions and motions of the artificial satellite against the background of fixed stars. And on the resulting photographic plates, an entire sequence of positional data is obtained, which can readily be reduced by trigonometric means. An extremely accurate statistical averaging procedure is used, which involves the measurement by an optical comparator of many such photographically recorded positions of the satellite with respect to the stars, and the subsequent reduction of these data on high-speed electronic computing machines, into which the satellite and star positions and certain other programming factors are fed on tapes. These solutions result in very exact geographic coordinates and altitudes for the positions occupied by the ground stations, together with the precise distances between these observing stations, without any necessity for traversing the intervening terrain. Scale control is achieved by a calibration of one side of the Earth-based triangle through a connecting densification network and by comparison with the Coast and Geodetic Survey's high-precision transcontinental geodetic traverse. Surveyed with an accuracy of 1 part per million by use of geodometers. The resulting accuracy in distance determination by the satellite triangulation method is at least 2 parts per million, and eventual accuracies may exceed this figure. Because the average distance of the ECHO satellite is about 830 miles from the surface of the Earth, the sides of the surface-based triangles used may be approximately 800 to 1,400 miles in length, and may easily place the respective observers in different countries of the world. When, therefore, a program was arranged with the Canadian government for cooperative satellite triangulation observations to permit the determination of more precise geodetic positions and the establishment of improved geodetic datum ties, it was a natural continuation of a long-practiced coast survey policy of participation in international cooperative endeavors. Demonstrating the extreme versatility and flexibility of the system, Canadian and American geodesists manned satellite triangulation units, flown into Cambridge Bay, Northwest Territories, and shipped by rail to an observing station at Lynn Lake, Manitoba, some 1,400 miles farther south. The Coast and Geodetic Survey established the third point of a triangle at Whitehorse in the Yukon. Transporting the equipment on an open flatbed truck over 3,000 miles of highway from a staging point near Santa Ana, California, to test the durability and complete mobility of the equipment. Northward, the carrier rolled with its valuable cargo across the Canadian border, thence by way of the glistening white thread of the Alcan Highway into the Canadian Northlands. Measurements across rugged terrain, which could take a field party working with a geodometer many months to traverse, were shortly to be secured in the split-second timing of a satellite triangulation camera. Into the territory of the husky Malamute, a crude but often indispensable dog sled, the ever-practical log cabin. Then on to Whitehorse, Yukon, offering a fascinating modern insight into Alaskan gold rush days. Here in this wilderness empire, a miracle of modern science was established. The satellite camera equipment was unloaded from its truck carrier and erected upon a vibration-free pier over a marker permanently emplaced in concrete. The Astrodome used to house the camera is light, compact, manually rotated, and relatively uncomplicated to permit ease in transportation to worldwide observing stations. The Astrodome houses the BC-4 satellite camera, which is simplified by the omission of star tracking mechanisms, but through the precision of its mechanical and optical systems, yields an accuracy of better than 1/2 second of arc in the positional determination of the artificial satellite or a reference star. To permit subsequent time reference measurements of the objects photographed, it is desirable to record point images on the plate rather than drawn-out exposure trails produced both by the rotation of the Earth and by the satellite's motion in orbit. Accordingly, the Before and after each satellite tracking event, an external camera shutter is used to chop the photographed star trails into a series of point images. The external capping shutter is activated by a programming tape and a time code generator to provide an effective shutter opening rate ranging from 1/2 to 5 exposures per second. As the satellite itself crosses the field of view, 2 high-speed, contra-rotating disc-type shutters and 1 slow-speed capping shutter located between the camera lenses likewise chop the satellite images, producing a regularly spaced series of point images. Occasional identifying gaps are also introduced in the series by the auxiliary chopping action of the external shutter. The resulting photographic plate contains such interrupted star and satellite trails. The satellite trail is coded to facilitate image identification with respect to time. The coded star trails are also given different exposures to optimize the image size for both faint and bright stars. The exposure of star trails before and after each satellite passage permits determination of the camera orientation and satellite direction. Within the protection of the instrument shelter is the complete electronic control system for the satellite camera, a system providing camera synchronization with a time source common to the 2 or more observing stations. One of its major functions is to monitor and record the electronic pulses corresponding to the precise instance of each full opening of the internal camera shutters. The center of each recorded satellite image is thereby electronically timed within an accuracy of 1/10,000th of a second. The precise instant of each full opening of the internal shutters is determined by synchronizing on an oscilloscope the shutter pulse from the camera and the shutter gate pulse from the time code generator within the previously specified accuracy of 1/10,000th of a second. Time synchronization between the various observing stations and the United States Naval Observatory, or the National Bureau of Standards, is achieved by flying a high-precision, portable quartz crystal clock to each station. Timing pulses from this clock, accurate to within 10 millionths of a second, as calibrated from the master clocks in Washington, D.C., are fed into the oscilloscope and are compared with the timing pulses generated by the console. At this Northland base, these and other tests, continuous, exacting, rigorously performed by checklist, were conducted in preparation for the actual operational trials. During the day, the camera plate holders were loaded, brought to thermal equilibrium with the atmosphere in anticipation of each clear night of observation. At night, extensive photographic runs were made on the star Polaris for the purpose of precise camera orientation until the satellite triangulation facility at Whitehorse and the supporting units at Lynn Lake and Cambridge Bay were in every respect checked out and ready for the cooperative program. And then, finally, came the eventful night of action and the rendezvous with the artificial satellite, Echo. With the object's orbital characteristics and the optimum times and positions for observation having previously been made available in tables provided by the National Aeronautics and Space Administration to the observing station, all was in operational readiness. The main power switch was thrown. Motors hummed. The electrical system came up to peak power, and electronic tube components warmed into life. Outside, in the Astrodome, the satellite camera was directed toward the desired intercept point in Echo's orbital path, and pinpointed to this position by precise optical procedures. 10-minute warning. A final alert was passed to clear the Astrodome. The switch providing power to the internal shutters was closed. Timing synchronization was achieved. The external capping shutter was activated to time code the satellite trail, and the internal and external shutters combined to provide a non-rhythmic staccato movement. And then, across the velvet blackness of the night, a small luminous spot moved swiftly. Upward it sped from the horizon to intercept with its predicted rendezvous position. Final checks were made at the controlling console to ensure an accurate record of the event. Then, capture, as the satellite entered the camera field of view, while, in the instrument shelter, men and machines were recording the precise instant of its passage. Swiftly, the satellite crossed the magnified field of the camera. Its image trailed to the edge of the field and as quickly disappeared from view. With split-second precision, the camera has performed its intended function in recording the time-referenced positions of the satellite against the background of fixed stars. And in two other locations, approximately 1,000 miles away, identical cameras have performed an identical role. Tonight's observation has been accomplished. By teletype, a report is transmitted to headquarters in Washington indicating the successful completion of the work. Subsequently, the relative positions of the artificial satellite with respect to the star field photographed at this station will be analyzed, and the results will be compared by electronic data processing methods with the respective positions of the same objects on photographic plates obtained at the other two satellite triangulation stations. Ever-widening satellite triangulation surveys conducted in this manner will be linked. And from this effort will eventually come the possibility of intercontinental datum ties. To ensure optimum planning and coordination, the results of each step of this program are analyzed, discussed, and applied to the development of new, practical, and additionally productive uses of satellite geodesy. One of the definite scientific advantages which must accrue from these surveys is the establishment of a more adequate deep-sea geodetic control for such navigational and position-fixing systems as Loran-C, employed in oceanographic surveys. This will result in a corresponding increased accuracy in the locations both of ocean floor features and ocean survey stations. The theoretical procedures and mathematical techniques of satellite geodesy also open the way to the use of photogrammetry from orbit as a means of achieving precise measurements of the surface of the moon or more remote planetary bodies. These measurements will be obtained by using special sensors attached to environmental survey satellites, such as the proposed Environmental Lunar Excursion Module Laboratory. Photogrammetry from space may be accomplished on lunar surface features, which, because of their heights, ruggedness, and vast lateral dimensions, would present a particularly difficult task for ground traverse surveying. In addition, using data gathered from the satellite triangulation program, the mathematical figure of the Earth, known as the reference ellipsoid, can be re-evaluated. And Through cooperative scientific programs concerned with the distribution of mass within the Earth, a better determination of the true figure of the Earth, known as the geoid, can be achieved. This knowledge will in turn facilitate the scientific interpretation of gravitationally induced deviations, termed perturbations, which are observed in the orbits of artificial satellites. A quantitative determination of the factors producing these gravitational disturbances becomes indispensable for long-range satellite orbit predictions and associated problems, such as precise rendezvous, docking, and resupply missions in outer space. And so, the insatiable quest for more complete knowledge of the world on which we live goes on. Man's desire for greater understanding of his planet impels him to search over expanding horizons and into new fields of scientific endeavor. In this research into ever-broadening aspects of man's geophysical environment, the work of geodetic scientists will form an exciting, important, and continuing role.
You know, a lot of our viewers have written in with one big question. They want to know the difference between our basic celestial navigation tape that you just finished watching and our regular celestial navigation tape in our Safe Boating series. Well, here's the difference. They're both 2 hours. Now, the one that's from the Safe Boating series only has 2 lectures. I do the first lecture, and it's basically the theory, what to measure, why you measure it, how you measure it, what you do with the measurements, all the abbreviations, all the definitions, GHA, GMT, GP, and things like that. Then the second lecture is done by Paul Miller, who used to instruct at the United States Naval Academy in Annapolis. And Paul spends a great deal of time showing you how to use a sextant, how to hold it, how to look through it, how to adjust the mirrors, how to read it. And then he tells you what to do with all the readings, how to fill out the worksheet to do a noon shot. That's just the sun. And it doesn't mean 12 o'clock watch time necessarily. It means local apparent noon when the sun is directly above your meridian, that precise second. You use the sextant to get the measurement, find out when it's right above you, and mark the exact second. Then you just look it up in the Nautical Almanac, and whatever the longitude of the sun was at that time, that's your longitude. And then Paul goes to show you how to fill in the rest of the blanks on the worksheet, because you've got your measurements from your sextant, to show you how to get your latitude. So all that tape gives you is how to do the basic celestial noon shot of the sun at local apparent noon. It's more or less for beginners because it gives a good background on how to use the sextant. On the other hand, the program you just watched was 4 lectures, and it went into the horizon, the intercept method, how to use HO 249, the Air Almanac, and of course how to solve the celestial triangle. If you really want to get a good handle on celestial navigation, we suggest that you have both tapes in your library. And if you have any difficulty finding the other one, well, just check with the same place where you got this tape. And if they don't have it, get in touch with us, and we'll surely tell you where to get the other one. Thank you very much. Happy sailing, and remember, safe boating is no accident.